Hello, this is Jack Jackson. In this video, we're going to talk about compositions of reflections. We actually started talking about this in the last video, which is an older video I put together using some Geometry Sketchpad resources. This is going to use a more advanced, newer creation in GeoGebra to help us investigate this in a little bit more detail. So we have defined a glide reflection as a composition of a translation by a vector followed by a reflection about a mirror line parallel to that vector. But other composition of isometries are possible. We've already looked at reflection followed by another reflection in some cases. There also could be a translation, then a rotation translation, reflection translation, rotation reflection, rotation rotation, and so forth. Lots of different options. And we will ultimately examine all of these in some detail in this playlist and in this chapter. And earlier we proved that a composition of two isometries is another isometry. And potentially it seems like this could give rise to infinitely many different types of isometries as we keep composing more and more isometries. However, it turns out that all of these isometries can be attained by a single transformation of one of the following five basic types: identity transformation, translation, rotation, reflection, or glide reflection, all of which we've already talked about. We will investigate composition reflections carefully and prove this result. We have also already proved that we can generate all isometries by starting with reflections alone. In the next big investigation, we will see what happens when we compose one, two, or three reflections. We will carefully examine each case, and we will see exactly how the identity transformation or reflection, rotation, translation, or glide reflection is obtained in each case. Since we have already shown that every isometry is obtained by the composition of three or fewer reflections, and the following careful investigation shows that only the identity transformation, translation, rotation, reflection, or glide reflection can result in the composition of three or fewer reflections, then these five types of transformations must be the only types of isometries possible. In the next few sections, we will look more carefully at the details of other various types of compositions of isometries as well. Let us start by examining what happens if we compose two reflections about lines in the same plane. There are three cases to consider. Depends on the placement of the mirror lines. The two mirror lines could actually be the same line. They could be distinct and intersecting, or they could be parallel. We are limiting our view at the moment to a single plane. Thus far, we have proved that any isometry can be obtained by the composition of up to three reflections. What possible isometries can three reflections compute? What different conditions on the relative positions of the 1, 2, or 3 mirror lines produce different transformations? The following activity that I created explores this question. If we open this activity, I encourage you to open it yourself and experiment with the various different options until you can discover the results, and you have convinced yourself that the conclusions in the activity are valid for every possible case. There are several multiple cases depending on the relative positions of the lines, and after manipulating the options in all the cases, you should have noticed that each product, composition, results in a single isometry, which must be one of the following types: identity transformation, translation, rotation, reflection, or glide reflections. And we can start with some of the details. The first one is, well, it's pretty obvious. If you just have one reflection, the result is a reflection. So obviously a single reflection is a reflection. So what if we do compositions of two reflections? So let me pull up my activity here. And there are several options that we may have. The second line could be the same as the first line. So here's mirror line 1. What if it's the same? So the first image, when we reflect over that line, is this image here. This is dynamic, so I can manipulate the points of the pre-image, and I can manipulate the mirror line. Okay, so we see that it's image. But what happens when we reflect it back over the same line? What's going to happen? What's the second image? Well, if you look, the second image is the same as the pre-image. So the ultimate result of reflecting twice is it's exactly right back where it started. The second image is the same as the pre-image. A prime equals B prime, A, B equals B prime, C prime equals C, or in this case, I called it double prime here. So if we reflect it on the same line twice, we get the identity transformation. So pretty simple proof. How do we go about actually formally proving that? Well, let's see. Let's look at the picture up here. When we go across here, let's take A to A prime. Remember that when it's a reflection, that let me do it this way. Let me show you. Just show it to you here. If we connect up the line segment from pre-image to image like this, then the midpoint of that line segment is on the mirror line, and this line segment is perpendicular to the mirror line. That gives you the image A prime. Well, it's going to have to come back here because, again, the line segment that goes, if you take the distance from A to this point perpendicular here and continue the same distance over, you get the same line segment back that you started with. Okay, so that's the first case. So we can view a identity transformation as a reflection, composition of two reflections where the mirror line is the same for both reflections. Or if you want, just think of it as zero reflections done, and that's nothing's done. That's the identity transformation. Okay, so what's the next case? Well, the second line could be parallel to the first line. So here I can change this, but this line has to say parallel. Well, the intermediate image is going to be a reflection over the first line, and there's the line segment connecting up the pre-imaged image. And now where's the second image? We're going to reflect this one back over this line. Let's see, let me make this a bit closer. Now reflect that one over there. That's interesting. So how does the final image compare to the first one? Can you tell by just looking? What do you think? Is it a reflection, rotation, translation? What? Well, hopefully you can see that that is a translation. And one way, the easiest way to find out that it's a translation is to connect up pre-image to image point. Notice that in this case, all of the line segments are parallel and the same length. So the conclusion is that you get a translation. The vector that connects pre-image point to image point is this line segment with the arrow on the correct end. Notice those are all parallel and the same length, so they are the same vector. It is a translation. Now, how far is it translated and how does it compare to the mirror lines? Well, do you notice, what do you notice here? If I change this up, what happens? What happens when I change up the mirror line here? Do you notice that the mirror line, that the vector is always perpendicular to the mirror line? Now, I've measured some distances here. This distance between the two mirror lines, this perpendicular distance, is a 5.01, and that the distance between A and A prime is 10.02. Okay, actually all these distances is 10.02. What if I make this longer? 7.3, 14.6. It looks like it's twice as much. Okay, does it make a difference where we put this? So let's say, what if we put it on this side? Okay, now notice that the direction is in the direction from the first mirror line to the second one. course, it degenerates to the same image when they're the same. So that is in the direction from the first mirror line to the second, and sure enough, it is twice the distance between the two lines all the time. Okay, so when we reflect a pre-image over a mirror line, to reflect the intermediate image over a line that's parallel to the first mirror line, the result is equivalent to a single translation by a vector that's in the direction from the first mirror line to the second mirror line and perpendicular to both mirror lines. The length of the vector is twice the distance between the two mirror lines. So let's see if we can prove this. Here's the proof. When we reflect a pre-image point A over the mirror line, by definition, we obtain an image A prime here, such that this line segment from A to A prime is perpendicular here. And it's actually perpendicularly bisected by that mirror line. So that means the distance from A to X is the same as from A prime to X. Now, assuming the first mirror line does not contain A, we reflect A prime over the second mirror line and find the final image A double prime. So let X be the midpoint here and Y be the midpoint of this one here. All right, let's think about what we've got here. The distance from A to A prime is going to be twice the distance from A to X. And the distance from A prime to A double prime is going to be twice the distance from A prime to Y. So if we add these, this is, say, call this little distance, D, and this is D1. This is another D1. This is a D2. This is a D2. So this is D1 plus D2 is the distance from M1 to M2, and twice that will be the distance across here. And there are several cases to consider depending on the relative position of these things. So we already looked at this condition here. What if it's on this side? The relative position of where these pieces are. But if we chase through all of the different possibilities there, it turns out that this always works out. Okay, so let's see what we've got. Since both mirror lines are parallel, both the line segments A to A prime and A prime to A double prime are perpendicular to both mirror lines. That makes A prime, and A double prime collinear. And if they exist, X and Y are collinear with A prime, and A double prime. Furthermore, the line segment from A to A double prime is perpendicular to both mirror lines. XY is the distance between the two mirror lines. We know that X is between A and A prime. And now we have to chase through the different conditions. Okay, there's several of them to work through. Okay, so subcase 1. Suppose the first mirror line contains A. Only thing we really need to be concerned with is A here, not the rest of it. But the rest of it helps us kind of see what's going on. So in this case, what happens? A double prime, or A prime is the same as A. So A to A double prime is going to be twice the distance from here to Y. So again, twice the distance of between the lines. So that works out. What about the second mirror line contains A double prime? I've got these, I think, backwards. Contains, yeah, first one contains A. Suppose the second mirror line contains Okay, here's the appropriate picture for this. The second mirror line contains A prime. Well, in this case, the distance from A to the final image is just going to be twice the distance from A to X, which is, of course, the distance between the two lines here. Okay, so it works in that case. All right, the next case is suppose the second mirror line contains A. All right, so let's see here. We reflect over the first line. We're back over here. And the second one contains A. All right, so what are we looking at here? The distance from A to A double prime, okay, has to be the same as the distance from A to A prime. The distance from A to A prime is twice the distance here between the two mirror lines. So sure enough, it works again. Okay, so now we need to consider cases where neither A nor A prime are on the mirror line. In these cases, A prime, A double prime, X, and Y are 5 distinct collinear points, but in particular, A prime, X, and Y are different. So there's going to be 4 cases to consider depending on the order of A prime, X, and Y. So the first one, we look at the order A, X, A prime, Y. They're all in a straight line. Right, we already established that. So we just got to see about the order. So here's the picture for that. Okay, so we go A, X, then A prime, Y, and then A double prime. Okay, so let's see what we've got here. Because of the betweenness relationships, we can add some things together, right? So if you go from A to A prime, and then add A prime to A double prime, that's going to be twice going from A to X, or A prime to X, yeah, plus twice going from A prime to Y. You can kind of see that from the picture, how that works out. We're using the betweenness relationships that are there to help us do that. So you can kind of see that from the picture. And so once again, the whole distance, you can see this one is the same as that, that one's the same as that one. So the whole thing is twice the distance between the two lines, just what you need. I'm going to leave the details of this one as an exercise, but I think I have the right picture here. A, X, then Y, then A prime. So here it is. Once again, we should see um, the total distance from here to the red one at the end has to be twice the distance here. This is a little more complicated. Look at these two distances being the same. Let's see. Yeah, and this one is the same as the original one. This time you have to do some subtracting to work it out. So I'm going to leave it to you to figure that one out on your own to work through the details. Okay? So use some subtracting of areas there, of links. All right, so similarly, I'm going to leave the last 2 cases as exercises for you to work out the details, but look at the pictures here. Use these to help you out. This one says we've got A, then Y, then X, then A prime. So here we want to show that the distance, again, the distance from A to A double prime, this distance right here, has to be twice the distance here. So think about what you know. You know the distance from A prime to X is the same as the distance from A to X. You also know the distance from Y to A double prime is the same as the distance from Y to A prime. And then use those to somehow show that this one is twice that one there. So you have to think about this a little bit and may have to add or subtract some distances to get this thing to work out. So I'm going to leave that as an exercise for you to work through. Finally, we have one more case. We have, these are in the order Y, there it is, then A, then X, then A prime. Okay, so again, I'm going to leave it as an exercise. What do we know? We know A to X is the same as from X to A prime here. Those two are the same distance. We know the distance from y to a prime is the same as the distance from y to a double prime. And we want to show that the total distance from a to a double prime, the final distance, is twice the distance from x to y. So again, you're going to have to chase through that a little bit. There's some work involved there, but I'll let you finish that up. But if you fill out the details of these three remaining subcases, then what do we prove? We prove that in every case, that two reflections about two parallel lines results in a translation. That translation is the same from the direction of the first mirror line to the second, and the length of it is twice the distance between the two lines. Okay, I've got several cases to this proof and to this investigation. What we've done is reflecting about two parallel lines. We'll come about, and we've done about the same line twice. Then the next one we'll come back and look at what happens when they're about intersecting lines.